So we'll consider first rolling some dice and then drawing some cards, and then we'll look at a situation involving some real data. So if I roll 2 dice, then I'm going to get a 1 through a 6. Wrong roll. Thank you, Danny. You got it. So I can either get a 1, a 2, a 3, a 4, a 5, or a 6. So say event A is getting 2 on the first one, and event B is getting 3 on the second. So the probability of event A, probability of getting a 2, well, there's only one 2, so there's a 1 out of 6 chance that can happen. And similar down here, the probability of getting a 3, event B there, that's also 1 out of 6. Now, what's the probability I get a 2, and on the second roll, I get a 3? And according to this formula right here, that would be the probability of a 2 times the probability of getting a 2, or 3, excuse me, if I already got a 2. And think about that for a second. Does it matter that you got a 2 first and then a 3 second? And the answer is no. The probability of getting a 2 is independent of getting a 3. That doesn't matter. So this probability right here is really the same thing as just what's the probability of getting a 3, right? So it's just going to be 1/6 times 1/6. This knowledge doesn't change anything. So if the extra knowledge, right, that if statement there, doesn't change an outcome or probability, then the events are independent. And sometimes 2 events are independent and sometimes they're not. It just depends on the situation. Is there any relationship between those events? And here there is no relationship. So sometimes the probability of A and B is just probability of B times the probability of A, but sometimes it's not. And so the safe thing to do is to always consider that it might be and then think about it. And that's kind of similar to this equation back here, that there might be an intersection, there might be something common, there might not. Always consider there might be, and it could be 0, so what? So some books talk about 2 different versions of these formulas, but in general, I think you should really not. Always play it safe. That's the version of the formula. So let's look at a different situation. Cards. So first, let's make sure we all know what playing cards look like. So here is a set of cards. We have 2 sets of black cards, and there's 13 in each set. So we have the black clubs and the black spades. We have the red hearts and the red diamonds. Ace is considered a 1 because there's one figure in the middle. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then Jack, Queen, King, the face cards. So we have face cards. We have number cards. Ace is kind of special. It's used in different ways in different games. But there are 13 cards in each suit, and a suit is either a club, a spade, a heart, or a diamond. So let me screenshot that. Yeah. So we know what we're looking at. So some things to consider here. Let's draw 2 cards. on to both. So we're not putting the card back in the deck. So, and let's say we are going to look at the probability of drawing a face card. And the probability of drawing an ace. Now, if that's just the first draw on each, the probability with no other information, probability of drawing a face card, well, there's 1, 2, 3 by 4, there's 12 face cards, and 13 times 4 is 52 cards in the deck, so it's whatever 12 out of 52 is, and I can just leave it as a fraction. Often with probability fractions, we don't bother reducing them, because either we're going to state it as a percent or a decimal, and not reducing them tells you the total number of things that can happen in the bottom, right? There's 52 possible cards. I'm just going to leave it like that for now. As far as an ace goes, there's 4 aces, so 4 out of 52. Now it gets a little more interesting if I draw the 2 cards instead of just 1 at a time on their own. So for example, what's the probability of first getting a face card and second getting an ace? So one way to think about that, that would be the probability of getting a face card times the probability of getting a face card. Oops, no, ace next. Second draw. If I already have a face card. And let's see what that means here. So we know the probability of getting a face card, well, that's 12 out of 52. And then times here, the probability of getting an ace if I already have, holding in my hands, a face card. Well, if I have a face card in my hands, I have less cards. Face cards are not aces, so there are still 4 aces there, but I have 51 cards. So just notice here, this probability right here is not the same as that probability right here, right? Just drawing an ace, not thinking about a face card, it should be 4 out of 52. But if we draw an ace, knowing we already have a face card in our hand, there's less cards in the deck. So that probability changed. So in this case, since I'm holding on to cards, these events are not independent. Right, this information mattered. So sometimes the information matters when you're thinking about an and situation. Sometimes it doesn't change anything. Like, well, I roll the second dice, it doesn't matter what I get on the first one. That's the idea of independence. Do we always need to know if 2 events are independent up front? The answer is no, but we always have to think about it anytime we have an if or an and involved. And then the other big thing we have to think about in probabilities is back here, whether they have something in common or not. So that idea of being disjoint. So that's a slightly different idea than being independent. All right, new example.